Thank you so much, Professor Hudoya and the organizer for inviting me to participate in this very important meeting. I would say it's a great pleasure because I have some special connection with your country. My father was born and grew up in Indonesia. So I always wanted to come to visit Indonesia one of the days with my friend. I'm pretty sure that will happen in the future. So I'm looking forward. I'm
Yes.
also very excited to hear that you have launched big effort in battery manufacturing. I'm very happy to see the Indonesian Battery Association for battery manufacturing. I think your country is making the right step in the right direction. I'm very eager to hear more progress from you. Today, I'm going to talk about sort of my perception of future energy systems and the relationship with energy storage, and also talk about next generation batteries. So this is the outline of what I'm going to say today. First, I will sort of try to paint a broad picture on why energy storage is very important for future energy infrastructure. I will very quickly go some very basics. I think most of you are familiar with, but some background information would be important to explain the direction we are going for the future. And then finally, I will talk about the next generation high energy battery materials and cells that are supported by the Department of Energy and the Battery 500 consortium, for which I serve as the director. I'm also very happy to see that Professor Shani Meng would also give a plenary speech today, and she's a fantastic lecturer. I'm pretty sure you will enjoy it. Um, in the last few years, we have seen tremendous shift in our thinking towards climate change and future energy infrastructure. I know we have been going through different phases in our shaking, but now I think the whole world is building on the consensus that we are moving to the direction very quickly to a new energy world in which most of the energy will come from renewable clean energy. So particularly two of the important things I want to point out. One is the electrification of the transportation sector. A number of years ago, when Tesla was launched as a niche market, it was confined to a very small community where people could afford expensive luxury cars. But today, that has changed. Many companies, many countries have launched plans to replace gasoline vehicles with electric vehicles. So that's a huge change. Tesla no longer is the only player in the field. GM, European countries, the three automobile countries, all have joined the race. So today, even Tesla saying they are selling $500,000 electric vehicles each year. That's a very small number. But in the next few decades, that number would be huge. I mean, depending on which scenario we are using, we could have anywhere from 1 billion to 2 billion electric vehicles on the road. That's huge. Another thing that's going to change is also the fact that today 70% of our energy comes from fossil fuels. That include gasoline, but many other things. Right now, we know in the future, we want to go to in the world, we want to make this upside down. We want the renewable energy like solar, wind, hydro, other clean form of energy to represent more than 70% of the energy sector. So these are the two biggest change that would take place and would have tremendous impact, not only on technology, but also on the way we are living today. So the topic today is energy storage. I would like to try to convince you, maybe you are convinced already, that energy storage play a very critical role, not only in the unification of the energy infrastructure, but also in the whole energy market sector. Today, if we look at how we are consuming our energy, more than 40% goes to the electricity utilization, electricity we use in the household, in the manufacturing plant, etc. 30% goes to transportation. So what we are talking about is that both of that goes to renewable energy, and that cannot happen without energy storage. So I don't want to spend too much time to talk about what could possibly be the future energy infrastructure. But it suffices to say that today we have a centralized energy system with centralized energy generation, centralized power line, and centralized utility that controls how we use electricity, how we are paid the electricity price. But to the future, this is going to change for a number of things. One, it's not going to be centralized generation system. It's going to be distributed generation system, right? So you will have generation, big wind and solar farms, but you would also have energy generation at home. So it's going to be widely distributed system. Another thing that will happen is today we need to have something called a base node that's supplied by the centralized power plant. But with the base node capacity should be somewhere from 50% to 60% of the total generation capacity to maintain the stability. But in the renewable world, in the distributed world, that's not going to be there anymore. You don't have the security of the base node. The base node essentially need to be replaced by energy storage, or in a lot of times replaced by batteries. So what we're talking about is distributed variable generation system with huge amount of generation capabilities. Another thing that need to happen is also how to manage the system. There's a huge amount of data that we need to deal with to predict and control how this system work. So this is a picture, what I call energy cloud, that in which the generation, energy utilization, energy storage, and the data are highly integrated in a multiple way, not a one-way system. And plus, we'll also have not all electric vehicles that will discharge from the electrical grid. So this is something very difficult to work out, but it has to happen. It's a very exciting and very important direction for us to go. Now, has this happened in the past? Yes, it has. It has happened in the telecommunication market. I actually work at AT&T Bell Labs at the time that we had a centralized telephone system that essentially AT&T's logo at the time is one country, one company, one service. They have control of the centralized telephone systems, telephone lines, and control everything. And we pay huge dollars for example, international phone calls, a few dollars per minute. We pay by the number of minutes. Now, in the last 2 decades, what happened is the telecommunication market has been digitized. That's one thing. Another thing is the wireless technology. So that made it unnecessary to have or a sort of outdated to have a centralized system. It become a distributed system. Everybody can provide service in the market. To the end, we get a much better service, and we can go to many different companies for phone service, for data service, for internet, for entertainment, and we don't pay the service by minutes anymore. We pay for the quality of the service. We pay for the number of services we want. So that was a huge change that has happened in the telecommunication market. What I predict, I begin to preach for this only this year, that similar transformation would take place in the energy market. Now, going back to energy storage, as I said, we need to have data storage, we need to have energy storage. Data storage and the data analysis, data science are the softer side of things, of the coin. The other side of the coin is the hardware, the energy storage. Now, energy storage, we know we have to talk about batteries. Battery today is still the main power for energy storage, although I'll probably have a slide to show that energy storage can be done by hydropower and other things, but the main flow is battery, particularly lithium-ion battery. We know how important this is, and in 2019, 3 scientists received the Nobel Prize for the invention or commercialization of lithium-ion batteries that today play a key role in our society, from our cell phone to electrical car and to medical and many, many other things. So very luckily, our team, the Battery 500 Consortium, has the opportunity to work with 2 of the 3 scientists, Professor John Goodenough and Professor Stan Whittingham, as KPIs on the program. They provided important leadership and guidance and mentorship to our team. Now, I just want to go very quickly the battery basics. Essentially, you have cathode and anode, and in the traditional lithium-ion battery, what happens is the lithium cation get inserted and deserted in the electrode and back and forth. So this is sort of the rocking chair concept, and this is the invention of Professor Stan Whittingham, many in the later 70s, that eventually not the same material get used, but the same idea get used in today's lithium-ion battery. Now, some of the common cathode material that we use, including lithium carbon oxide, that's been widely used in our cell phone because of the high volumetric energy density. Lithium iron phosphate, widely used in power tools, in energy storage because of structural stability. Lithium nickel manganese carbon oxide, or NMC, or lithium nickel carbon aluminum oxide, or NCA. Those are the 2 materials widely used for electric vehicles because of the high specific energy and lightweight. Now, for the cathode, the common material is graphite, and the graphite has limited capacity below 400 milliamp hour per gram. And it's important to note that the graphite, the anode material, normally does not store the charge, right? The charge is stored in the cathode and is served as a host during charge discharge. So the ability to reduce the anode weight or to increase the capacity of the anode would play a key role to improve the energy density, reduce the cost of lithium-ion batteries. The candidate for those include silicon, for example. Silicon has 10 times more capacity but the volumetric expansion is huge. It's more than 300%, as shown in the TM here. When you charge it, the essentially like a bracing, they bend and shrink. Therefore, it's very difficult to stabilize. However, great progress has been made, and the silicon is on the way to be commercialized. Another important option, probably the most sort of important one today, the holy grail, is to use lithium metal as the anode material. Lithium metal by itself has the highest capacity as an electrode material and has the lightest weight, therefore has the biggest potential to reduce the weight of the cell, increase the energy density. So this chart shows the different options we have for different applications. And I'm just going to skip a lot of information. As I said, the commercial lithium cells are graphite and either AMC or lithium carbon oxide. And graphite, lithium iron phosphate, they don't have the highest energy density, but they are very stable. Therefore, they are widely used for energy storage today. Now, the graphite lithium carbon oxide is the one we use in our cell phone, and the high nickel AMC system or high capacity lithium carbon oxide or NCA system are the ones we are using for electric vehicle. Hopefully, we can replace anode with silicon. For doing that, we have a chance to increase the energy from traditional lithium batteries, about 200 watt-hour per kg to 300 watt-hour per kg or so. Now, to go beyond that, that's going to be very difficult. We have done a lot of analysis together with DOE and the community, and we think the future to gain the highest energy density, we have two options. One, lithium metal anode with high nickel AMC. One, lithium sulfur, lithium anode with sulfur. Both of these have potential to get to close to 500 watt-hour per kg. And the difference between the two is the AMC system has a higher volumetric energy density, and lithium sulfur system may have a higher gravimetric energy density, but both of them are very interesting to study. Another thing related to this is the sort of the cost. The energy density is closely related to the cost. Today's lithium-ion battery used to be about $200 per kilowatt hour. Now that was last year. This year is close to $100 per kilowatt hour already, and that's great for many applications. But for transportation, energy storage, we want the cost to be even lower, much lower than $100 per kilowatt hour. What are the options for us to do that? Again, that goes back to the kind of energy density. The higher the specific energy of the electrode material, capacity of the electrode material, high specific energy, and the less costly material we use, and the cheaper the battery can be. So the way to achieve ultra low cost batteries are to get to the high energy battery, not only with high energy, but also non-cycle life. So with that, this is sort of the projection from DOE throughout the years. Today, the number is already much less than $200 per kilowatt hour, edging towards $100 per kilowatt hour. But in the future, in the next few years or 5 or so years, that number has to get to less than even less than $80 per kilowatt hour. And the option for that is to use lithium metal, as I said, with a high nickel AMC cathode material with lithium anode with a sulfur cathode. And the long-term DOE goal, this is shown in the DOE energy storage grand challenge. You can find it on the internet. The report is out there. For long-term energy storage, it's not only get to the cost down, the capital cost down to much less than $100 per kilowatt hour, but also levelize the cost. I will probably explain that very quickly to less than 5 cents per kilowatt hour. About 5 cents per kilowatt hour is the electricity cost for many regions in the US. So the energy storage cost has to be on par with the electricity cost we are paying today. For transportation, the goal is to get less than $80 per kilowatt hour. And sort of electricity costs, I don't want to spend a lot of time on this, but it's essentially you take the capital cost of the battery, for example, it's like $100 or $200 per kilowatt hour. You roughly divide by the number of cycles you can achieve, and also compounding the round trip efficiency and other things. Then you get the life cycle levelized cost, the electricity cost. So if you take lithium-ion batteries, if you say it's $200 per kilowatt hour in cell level cost today, and add other things, and if you in traditional battery, you can do about 1,000 cycles or so. That's equivalent to more than 10 cents per kilowatt hour. So that's not sufficient for bulk energy storage market. You need to increase the cycle life. A few thousand cycles would be sufficient for electric vehicle application, but not sufficient for energy storage. For energy storage, you need to do more than 10 years, more than 10,000 cycles. In that case, the electricity cost would be just a few cents per kilowatt hour, as we are showing here. And the sort of I put all the different material we have today on the same chart to show where we need to go. Lithium-ion batteries with AMC NCA system can get close to less than $200 per kilowatt hour, and roughly less than 5,000 cycles. We need to reduce the cost to much less than $100 per kilowatt hour. But for energy storage, the main challenge is to take the same type of battery chemistry and make it last much longer, more than 10,000 cycles. Then we get a few cents per kilowatt hour. Now, with that as a background, I want to show you what we are.
Prof. Liu, excuse me. You have 5 minutes more for your
okay. I will be done in 5 minutes.
Yeah, thank you.
Okay, so I just want to end up with where we are going. I kind of try to paint a big picture on what we need to do. Now, what's our approach to get to the ultra low cost, ultra high energy density? That's the goal of the Innovation Center for Battery 500 Consortium. It's made of many universities and many national labs. It's a multi-year program, 5 to 10-year program. The goal is to increase the energy density to 500 watt-hour per kg with more than 1,000 cycles. And we have two battery chemistry we are studying, lithium metal anode with AMC and lithium sulfur. Now, what's fundamentally different for this program is that we are not only doing battery materials research, we are developing the best battery materials in electrolytes, and then we put them into the best designed real batteries, real pouch cells, manufacture the pouch cell, and demonstrate and validate the performance. If it doesn't work, we try to find out what's wrong on the whole cell level, and then what's the approach to improve it. So I will just skip most of the things. but show you two examples. One, we take the cathode material we are studying for lithium-ion batteries, but to use it in the high energy cells, we need to stress the material to the extreme. When we do this, for example, if we have very long cycles, the particle begin to degrade. We begin to have a surface transformation. Then we have a big team, including Professor Shani Meng here and Professor Stan Whittingham, many others, Professor Mainstrom. They try to find ways to solve this problem, degradation problem, to stabilize the cathode material. For example, putting surface coating on the surface so that we don't have this kind of degradation on the electrode level. Right? That's one thing we do. Another very important thing we do is we are using lithium metal as an anode. Lithium metal is very difficult. It's very sensitive. It reacts with everything. So we all know about the dendrite problem. But the dendrite problem mostly has been studied in sort of coin cells and idealized situation. We don't really know in a real cell what happens. So these are the examples of what happens to the lithium metal anode in real pouch cells. So we have a lot of details that I will not go through, but essentially you have a start with dense lithium metal anode, and then you begin to strip and deposit lithium metals on the surface. They become granularized, become particles, and then the particles get extruded, redeposited. They become more and more porous. So what we need to do is to develop new battery cell configurations, new electrolyte material, new surface protection method to prevent this kind of degradation and dendrite formation on lithium metal anode. So it has been lots of effort in the last 4 years from the team members, many students from the university, postdocs, staff members from national lab, for us to come to where we are today. So we started with high energy pouch cells, more than 300 watt-hour per kg, much higher than even our benchmark is much higher than what we could do in lithium-ion batteries. At the beginning of the program, just 4 years ago, we could only get 50 cycles. You can see the progress we are making today, and this chart is already outdated. For 300 watt-hour, 50 watt-hour per kg cells, we can already have very stable cycling for very close to 1,000 cycles. That's exactly what we are shooting for. And in the next 5 years, we are making plan for the next 5 years. We will take advantage of the progress we have been making. We want to increase. We already have data for much higher energy, but we not only need to get high energy, we also need to get long cycle life with high energy. More importantly, we need to make sure the batteries are robust, reliable, safe for commercial use. So that will take not only our whole team. I think we would also work with the whole community. Hopefully, we will find a breakthrough that will overcome today's limitation of the lithium-ion batteries. So that's the end of my presentation today. I want to summarize to say that energy storage is very important. I don't think you need to be convinced on that. Lithium-ion batteries still have a lot of room. I do not talk about that too much today, but we need to do safe, make it safe, fast charge, cost cycle life, material supply chain, manufacturing, all those things. But for next generation, we believe lithium metal batteries have the best chance, and we have made a lot of progress already on our team, thanks to all our team members and DOE support. But we still need new fundamental breakthroughs in the next few years. Thank you. I will stop here.